So this video looks at carboxylic acids and their derivatives, which is a large topic in the A-level organic chemistry course. So just to start, just as have a little exercise, and I'd like you to, pause the video to do this, but I want you to list everything you currently know or you think you can deduce or work out to do with carboxylic acid. So there are certainly, major elements of this topic that build or feature things that you've done in other parts of the A level. So I'd like you to just pause the video and just on a piece of paper or something list everything you know or you can work out, deduce once you start thinking about it, to do with carboxylic acids. So naturally we're going to start with how we could recognise whether something was a carboxylic acid or not. What makes a carboxylic acid a carboxylic acid is the functional group, and that is, if we were writing it as a condensed structural formula, it would be recognised as COOH. So we've got here an example of propanoic acid, and it has the structural formula CH3, CH2, and then the thing that makes it a propanoic acid, COOH. Okay, and so then we have the first 5 sort of straight chains. So just to give you, give you that sense of how you build up names and so on. So we've got 1 carbon, so it's meth, 2 carbons, so it's eth, and so on, right? And then the oic acid is what tells you that this is a carboxylic acid. In all of these names, we've got the an, so it says methan, ethan, propan. So the an is telling you that the rest of the molecule is saturated. So it is possible for something to be pent, and then we'd obviously need a number like pent 3N oic acid, and it could have a carbon double bond there on the 3rd carbon. So, or it would have, sorry, in that example. So anyway, it's the oic acid that shows us that it's a carboxylic acid, and the COOH also if we write the condensed formula. And then if we are looking at the sort of slightly more structural formula where we're showing some of the bonds, then you can see in the bottom right, the COOH refers to this here. So we've got a carbonyl group. So we had a carbonyl group in aldehydes and ketones, and what we learned about the carbonyl group, or some of what we learned about the carbonyl group when looking at aldehydes and ketones, is going to be relevant to our carboxylic acids, as we'll find out. So you have the course has featured carboxylic acids before this point. It primarily appeared when we did alcohols and looked at the oxidation of alcohols. And if you had a primary alcohol, it could be oxidized all the way to a carboxylic acid. It needed to be a primary alcohol, of course, for that to be able to happen. And carboxylic acids feature quite a lot in everyday life. So you may have noticed that there are a variety of vinegars, and you can have red wine vinegar, white wine vinegar, cider vinegar, sherry vinegar, etc. And what we've got here is we've got those alcoholic drinks that have ethanol, and the ethanol being oxidized to the carboxylic acid, ethanoic acid. So vinegar is essentially ethanoic acid. There are carboxylic acid groups, or there is a carboxylic acid group in aspirin, and that one of the features of this topic is there's a core practical where aspirin is synthesized or made by you, and so this structure in the bottom left here would be something that you would make as part of your core practical. There's a reminder there about vinegar being ethanoic acid. Citric acid, so in citrus fruits, notice actually it has 3 carboxylic acid groups in its structure. And in ant bites, there is methanoic acid. The old-fashioned name was formic acid, and that formic part came from the Latin for ants. So formic acid, or sorry, methanoic acid, I should use the correct UPAC name. Methanoic acid is in the bites of ants, and also in the sting of nettles. So there's also methanoic acid in that. And it's quite useful to see that you've got that hydrogen, you've got a hydrogen bonded to the carbonyl. I think it's quite useful to see that it's because the carbon of the carbonyl is one of the carbons that you count when determining the name of a carboxylic acid, we can see why it's methanoic here, because there is one carbon and it's the carbonyl carbon. Now the physical properties, we've had an insight into the physical properties, or at least about boiling point, to do with carboxylic acids, again when we did alcohols, because if you remember, if we were oxidizing a primary alcohol, before it became a carboxylic acid, it would have become a aldehyde. And if we wanted to just make the aldehyde, or we wanted to just extract the aldehyde, or it was the aldehyde we were interested in that reaction, then we needed to basically remove it from the reaction mixture, remove it from the oxidizing agent, which was the potassium dichromate, before it got to be oxidized any further. And the way that we were able to do that, or the reason we were able to do that, was through distillation, because the aldehyde had a much lower boiling point than both the alcohol that it was produced from and the carboxylic acid that it could potentially have become if it was oxidized any further. So we know that carboxylic acids have a high boiling point relative to the size of molecule that they are. And when we were explaining being able to extract an aldehyde through distillation and relying on the boiling point, we had to basically explain why those boiling points were different. So with an alcohol, we knew that there was hydrogen bonding, and with the carboxylic acid, we knew there was hydrogen bonding. But with the aldehyde, it was just permanent dipole-dipole, and the molecules would naturally be roughly the same size. So the van der Waals interactions weren't dramatically different. So it really boiled down to, sorry, that was a bad pun, but it really came down to the fact that we had hydrogen bonding versus permanent dipole-dipole. And so that explained why the aldehyde had a lower boiling point. So we know that the alcohol and the carboxylic acid have hydrogen bonding, but what's interesting, if you look at the example we got on the screen here, so we've got ethanoic acid and propan-1-ol, is that actually the ethanoic acid has a higher boiling point. And actually, 20 degrees is a reasonably significant difference. So just thinking about why is it, if they both have hydrogen bonding and they both have a very similar MR, why is it that the ethanoic acid has a 20 plus degree higher boiling point? So I want you to just pause and maybe have a think about that, and then we'll look at the reason behind it. Okay, so there's a structure of our ethanoic acid, and what I'm going to do now is I'm just going to draw a second ethanoic acid molecule, and then I want you to then have a think about, is there something that you can consider there? Okay, so there's the second one. Now I have deliberately drawn them in the orientation that they are, so I'm hoping what you'll begin to realise, or you might be able to realise when you look at that, is that each ethanoic acid molecule can actually form two hydrogen bond interactions. So what we get as a result is something called a dimer, okay, because there's two parts to it. So that mer is like as in polymer, so parts, and then di, two of them. So there's two parts to it. And in effect, what's happened as a result is that we, it's perhaps stretching it a little bit far to say that we now have a bigger molecule, but what we will have between dimers are stronger van der Waals interactions, because we do have overall a larger sort of MR. So it really results in an increase or greater van der Waals forces, and those coupled with the hydrogen bonding just basically is the reason behind why ethanoic acid has a 20 odd degree higher boiling point than propan-1-ol. What about their solubility? Well, it's not a surprise, I shouldn't think, to know that carboxylic acids are soluble in water. I mean, if you think that citric acid, for example, is basically dissolved in water, you can get soluble aspirin, although actually not all aspirin is that soluble. So there are other factors to consider. So if we think about their solubility, it's not as simply, with solubility, it's very rarely a case of, oh, it's either soluble or it's insoluble. They're quite often degrees of solubility. Some things are very soluble, so that you can basically say they are soluble. Now with short chain carboxylic acids, then they are very soluble, and the reason for that is because of the hydrogen bonds that they can form with water molecules. Now the fact that we're saying short chain is important because what we have, we don't just have that carboxylic acid group, we have an alkyl, or typically we have an alkyl group if we go beyond methanoic acid. We have an alkyl group attached to that COOH, and that alkyl group is hydrophobic, basically. Okay, so it doesn't dissolve typically very well. Now, if that's a short chain, then we've basically got the hydrogen bonding dominating. But if that alkyl group that's attached to the COH gets, as it increases in length, then that is a very hydrophobic part of the molecule, and if that gets, as that gets larger and larger and larger, that tends to dominate, and then we would find that our carboxylic acids became increasingly insoluble, or much less soluble as that alkyl chain grew or got longer, and so the solubility would be decreasing. But equally, in that instance, they would become more soluble in lipids or basically organic solvents, such as cyclohexane or whatever. So just to bear in mind, I mean, most of the carboxylic acids that you're going to look at A level are going to be pretty soluble. Certainly when you're talking about ethanoic, methanoic and propanoic acid, you're talking about them being soluble in water. But just bear in mind, if you have a carboxylic acid where the alkyl chain is very long, then you're going to have something that isn't very soluble in water. And that actually will be relevant a little bit later in this video. Now, unsurprisingly, carboxylic acids are acids. The clue is in the name. And given that we consume citric acid, given that we consume methanoic acid, maybe your knowledge from GCSE, or even maybe you've done the acids and bases part of the A level, one of the things that you hopefully realise is that carboxylic acids are weak acids. And by weak acids, we mean they only partially ionize, which means that there is an equilibria reaction. So there is an equilibria of the undissociated and dissociated versions of the carboxylic acid. That means we can write an equilibrium constant. So if we look at the one above, which is, or the one on this slide, sorry, I say above, the one on this slide, which is ethanoic acid, now you just pause the video and write the equilibrium constant expression for that equation. So hopefully you wrote that expression. So on the top, we've got the H concentration of the H plus ions, and we've got the concentration of the ethanoate ions, and then on the denominator we've got the concentration at equilibria of the ethanoic acid molecules. And in something like ethanoic acid, approximately, I mean roughly about 2% of the ethanoic acid molecules are dissociated at equilibria under sort of standard conditions. I mean, it's just to give you a sense, an idea of where the position of equilibria lies. So it is quite far to the left, and that's one of the reasons why the concentration of hydrogen ions is quite low, or relatively low. So that explains why if we have 1 mole per decimeter cubed of ethanoic acid, why we might have a pH or concentration of hydrogen ions rather that is, roughly 100 times less than that of, say, hydrochloric acid at 1 mole per decimeter cubed. Now, given that carboxylic acids are acids, that means they will react in the way that we expect acids to react. So even though this is an organic module, and our heads can just be sometimes so just focused on organic, we can miss other aspects. You've still got to remember the standard equations of acids and bases. The standard, so acid plus alkali produces a salt and water, and acid plus metal produces a salt and hydrogen. So if we put magnesium, for example, we put a fairly reactive metal into a carboxylic acid, we would see fizzing, we would see effervescence, there would be hydrogen produced. One thing that you have done to do with carboxylic acids prior to this topic is how to test for them. And one of the things that you would use was a carbonate, so sodium carbonate, which is a soluble carbonate. So sodium carbonate and a carboxylic acid, and you would see effervescence, fizzing, because carbon dioxide would be produced. So you need to remember these sort of general equations and not get. It's sometimes easy to just lose sight of the fact that a question can be about the fact that it's an acid reacting with a base. Okay, so just bear that in mind when you're looking at questions in the future. So here are just now some sort of specific examples. So we've got our general equation of an acid and carbonate producing salt, carbon dioxide and water. So we just got ethanoic acid, sodium carbonate. So we get sodium methanoate, that's our salt. Okay, so sodium methanoate is our salt. We get carbon dioxide and we get water. Then if we look at the actual reaction equation, one thing I just want to highlight in particular at this point is how I've presented the salts. So if we look at the sodium methanoate, now you'll see that I've put the charge on the ethanoate ion and I've put the charge on the sodium ion. And in fact, if you look at the one below, which is an acid and a metal oxide, and I've deliberately done this, propanoic acid and magnesium oxide. So I've used magnesium, which is when it's an ion, it's a 2+ charge. So I needed 2 propanoates in this formula. You'll notice I put the charges. And I think probably if you were to look in, I don't know, textbooks or revision guides, I'm imagining, 80% of the time they will show the charges. And I think it's good for you to show the charges because I think it helps you just realise that actually you've got something where if the water's been evaporated, you've got an ionic compound. So it'll have a relatively high melting point. But also to recognise, though, that when it's in solution, you're going to have these sodium ions and these ethanoate ions completely separate, and to remember that ethanoate is an ion. But you will see formulae written without those charges. So you could see a formula of sodium ethanoate written something like, well, not something like, you could see it written like this. Okay, so just, that's not very legible, but CH3COONA. So just bear that in mind. I would like you to use the minus and plus charges, but don't be surprised if you see it without. We've also got the acid and alkali example here. So we've written methanoic acid just to give a little bit of variety. We've got potassium hydroxide again to give a little bit of variety, not to just be wedded to sort of sodium all the time. And then last one, the acid and metal producing salt and hydrogen. Okay, and just remember you've got to balance it in just as you would balance any reaction equation. So we've got 2 propanoic acids and 2 lithiums producing 2 lithium propanoate salts, and then the hydrogen H2. Okay, so just bear in mind your sort of stoichiometry, your molar ratios. All right, so everything up to this point has really been just thinking about carboxylic acids in terms of them as acids, and also in terms of their physical properties, and then thinking about how you name them or how you draw them or whatever. And another carboxylic acid that you are familiar with is lactic acid. And so obviously if you exercise and exercise for a while and there's not enough oxygen getting to your cells, then lactic acid is a product of anaerobic respiration, and it's also what makes milk taste sour. So if milk goes off basically and it tastes sour, it's lactic acid that you're tasting. And incidentally, actually, acid comes from the Latin word for sour, and that's how it was how they were first identified. So anyway, we've got lactic acid here. It's quite a sort of, it's a sort of molecule actually that does appear in exams, and it's not, I'm not saying it's been asked lots of times, but it wouldn't be an unexpected thing to be asked for you to give its UPAC name. So it could be a way of them getting you to name a molecule. So I want you to have a think about what the UPAC name for lactic acid is, and and I'm giving you a clue here to identify any chiral carbons. But are there any chiral carbons? In fact, I'm asking probably suggests there is. So can you find where it or they are? And then, importantly, to draw then the optical isomers if there are any chiral carbons. Okay, so its UPAC name is 2-hydroxypropanoic acid. So let's just make it clear that that is correct. So find what the longest carbon chain is. Well, the longest carbon chain is 3 carbons, hence the prop. We know it's got a carboxylic acid group. So let's just highlight that as the carboxylic acid group. But we also know, or we can also see that we've got an OH group. Now, carboxylic acids trump OH groups when it comes to priority in the naming, or which one becomes the suffix. So if there's a carboxylic acid group, it will be the suffix as far as your A level is concerned. So we've got the oic acid, at the end. And if the alcohol can't be accommodated in the suffix, because it can if there was an alkene. So if you remember, you could have something like you could have propen, you could have ethanol, actually. Let's use that because I didn't want to get into the pickle about the numbers. But anyway, ethanol. And so it was possible to still to have a second functional group and to keep the alcohol. But if you've got a carboxylic acid, you can't have the alcohol group in the suffix of the name. So it becomes hydroxy. That's a prefix version of the OH group. And then when we're counting, I mean, it is in the middle carbon, whichever direction. So you could incorrectly and correctly identify that it was the second, and therefore write 2-hydroxypropanoic. But one thing to stress, that just like with nitriles, your first carbon is the carbon of the functional group, which obviously is the carboxylic acid. So it's the carbonyl carbon is the first carbon when you're naming a carboxylic acid. Sorry. So did you spot, or have you spotted whether there are any chiral carbons? So actually, I'm just going to rub out the colours so that we can look at the chirality. So just that's what I'm going to do now. Okay, so the way we can identify a chiral carbon is if it has 4 different groups attached to it. And if we look at this carbon here, we can see that we have obviously the carboxylic acid group attached to it. We have the OH group attached to it. We have a methyl group attached to it, and we also have a hydrogen attached to it. So we have our 4 different groups. So the next thing for us to do is to draw the 2 optical isomers, and we're going to do this using the dashes and wedges, the three-dimensional approach. So we have a carbon with 4 different groups attached, which means it is going to be tetrahedral around that carbon. So if we draw the chiral carbon first, and then my advice is that you, before you start writing any groups, just draw the 3-dimensional shape in terms of the bonds. Just draw them like that. And then we've got 4 different groups to draw around. So make it as easy for yourself as you can. So COOH. Just easy to draw it like that. Love the H here, the alcohol. It doesn't really matter where you put them, as long as, it doesn't really matter where you put them. But just make sure, particularly with the OH, that it's the O that's bonded to the carbon. And when you're writing the COOH, make sure it's the carbon bonded to the carbon. And then we want to do the mirror image. So once we've drawn one, draw like a dotted line. That's going to be sort of our mirror image line. And then the thing to do is to draw the second tetrahedral shape, making sure it's a mirror image. So we need our sort of straight line on this, and then there's our H, and then we're going to have HOOC. So that's not very light. You see, actually, it would have been better if I'd drawn the wedge and the dashes and then added my groups. But anyway, hopefully that's made a point to you there. And then we've got our 2 optical isomers of our lactic acid or our 2-hydroxypropanoic acid. Right, so if you remember right at the start of the video, this topic is called carboxylic acids and their derivatives, and now we meet the first derivative, esters. So esters feature quite a lot in the final exams typically, and that's really because of, as we'll see, they feature in equilibrium reactions, and so they can feature in equilibrium questions. So this is where organic and physical can certainly cross over. And if you think about what paper 2 is physical and organic. So just bear that in mind, that even though we're going to be focusing on the organic aspects as we go through this video, just keep in the back of your head the whole sort of equilibria topic, because that can feature in actual exam questions too. All right, so again, like we started with carboxylic acids, we look at things like their general formula. So here we can see that we have what almost looks like a carboxylic acid group, because we have that C double bond O and then a CO. And then, but the difference is, and we've got the R group here, which that R on the left could be a hydrogen or it could be an alkyl group. But the thing to bear in mind here and is that the R dash, what that cannot be is a hydrogen, because the moment it's a hydrogen, then we do have a carboxylic acid, and we're not talking about carboxylic acids now, we're talking about esters. So you've got an R and an R dash. They could obviously be the same. They could both be CH3 or whatever, for example, and the R that's attached to the carbonyl group can be a hydrogen, but the R dash that's bonded to just to the oxygen with only single bonds, that cannot be a hydrogen, because then it would be a carboxylic acid. So when we're looking at condensed formula, we can recognize it by seeing COO in the middle of a condensed or structural formula, and then you've got R groups either side of, although the one before the COO could be an H, of course. So that's how we could recognize an ester. You can see that we've got a displayed formula here. Remember, with a displayed formula, you must show every single bond. Where people typically slip up is with a carboxylic acid or an alcohol, they just write OH and they don't write the O bond H, for example. And we've also got a skeletal formula of an ester there too. So making an ester requires, or is a reaction between an alcohol and a carboxylic acid, and that type of reaction is called an esterification reaction. So we've got an example there. We've got propane-1-ol reacting with ethanoic acid to produce propyl ethanoate, and we're going to talk about the names in a second, so don't worry too much about that just right now. And then water. As you can see, it's an equilibrium reaction. And the other thing to pay a note or attention to is the fact that it's catalyzed by concentrated sulfuric acid. So I could show that there was an acid catalyst by, over the equilibria sign, writing H+. But the source of those H+ ions is going to be concentrated sulfuric acid. You need to warm it. It says heat, but warm is probably a better way of thinking about it, because what you mustn't do is heat it with a Bunsen burner. So don't heat it with a Bunsen burner, okay? Why? Well, if you look at what you've got present in the reaction, you've got an alcohol. And alcohols are flammable. Also, even allowing for hydrogen bonding, these alcohols, carboxylic acid, still have a relatively low boiling point, so it's just too aggressive. You're not going to be able to control it. You've got volatile liquids, even with a reflux. If you heat it too vigorously, that alcohol or the reaction mixture can come out the top of the reflux, because it's not closed at the top, because obviously you need to allow pressure to be not build up, and then you could have a serious problem. So you warm it. It'll be a water bath, or you could use a heating mantle, which you could control more precisely, but you don't use a Bunsen burner. So esterification is an example of also of a condensation reaction. And I've got a sort of slightly strange sort of description or definition of what a condensation reaction is. So you've got two molecules coming together, and you might read that, and a small molecule is produced as well as the main sort of thing that you're looking for. But I'm going to use this word eliminated, and I think that's going to be useful later in this topic when we look at a new mechanism which is called nucleophilic addition elimination. And it's a smaller molecule that's eliminated. Quite often it's water, but it's not exclusively water. So even though it's called a condensation reaction, and then you think, well, that's got to be about the production or removal of water, it could be another small molecule, like, for example, HCl. So, and in fact, that will happen when we look at another derivative of a carboxylic acid. So, condensation reaction is a removal of small molecule, typically water. It's not typically water that's being eliminated when the two molecules come together, but bear in mind it could be another small molecule like HCl. All right, so naming esters is important, both to actually be able to name them yourself, but also to understand what a name is telling you. This first part I've written here, I've got on the slide here. Notice how the part in blue has the same structure as a carboxylate. That is true. However, they used isotopes to determine exactly which oxygens came from where when you had an ester produced from an alcohol and a carboxylic acid. And what they discovered was this part of the molecule came from the carboxylic acid, and this part of the molecule came from the alcohol. So that's how we're going to think about naming it. So the chain with the carbonyl is going to be the suffix. So we can see that with the chain with the carbonyl, it's 2 carbons, hence it's ethanoate. And then if we look at the remainder of the structure, so the part that's come from the alcohol, that's going to be the prefix. And we can see that's a 3-carbon chain, so it's prop, and simply then the name is going to be propyl, and then ethanoate. Okay. I just realised that actually the name was in the reaction equation below, but never mind. All right, so some more examples. So what I'd like you to do is I'd like you to pause the video, have a look at these, and decide what the names of each of these molecules is. So I'll just let the video run on a little bit, but then I'm just going to write the answers. So you're going to need to pause the video and, yeah, please come up with the answers to the names of these 4 different molecules, please. Okay, so I've highlighted just first of all the parts of the molecule that will have come from the carboxylic acid. That gives us the suffix name. So we can see then that the suffix part of the names of these molecules will be ethanoate, propanoate, ethanoate, methanoate. And then if we now look at the parts that came from the alcohol, that gives us now the prefix part of the name. So we end up now with propyl ethanoate, ethyl propanoate, methyl ethanoate, and ethyl methanoate. And now perhaps as a final exercise, could you write the sort of condensed structural formulae for each of these, please? So, you know, how you would write CH3, CH2, etc., etc. And there we go. So just notice, make sure you're happy with how you would have written these as condensed structural formulae too. Now, obviously, you can have much more complicated names than those we've just looked at, and this one is more complicated, although it's not shockingly more complicated. So we've got 2-methyl propyl ethanoate. So if I just colour in the parts to make that clear, so that's the ethanoate part. And then if we look at the propyl bit, propyl bit is there, and then if we look at the methyl, that's there. So it's not a massively difficult one. We've got the methyl group on the 2nd carbon of the propyl. I mean, it's actually arguable whether the 2 is necessary there. But anyway, you won't even get anything like that. So just make sure you're confident with coming up with basic names of esters, and you will be fine. Okay, so another little exercise for you, and this is a really useful one actually. So anyway, we've got a general or a molecular formula, sorry, of C4H8O2, and I want you to come up with as many esters that would have that molecular formula as you can, please. So it says draw the displayed formulae and name them. I'm going to, because I don't have a lot of space here, and I'm not. It's quite difficult with a pen to draw really clearly. So I'm going to do them as skeletal formulae, but you do them as displayed formulae, and then we'll look at their names. You've still got to name them. I'll name it, and let's then see if we get the same answer. Sorry. So pause the video and try and determine how many esters would have that molecular formula. So I got 4. Actually, the thing I'd hoped this was going to show us or allow me to sort of highlight actually isn't really here. But just be aware that if you have got, if you're having to draw an isomer of a ester and you're presented with something that's quite simple and you think, well, I really don't see how that could be any different. It's not quite relevant here. The thing to remember to do is to reverse the COOH. So I am just going to draw an example actually. So this isn't to do with this question here. We haven't done phenyl groups or benzene rings yet, but so we could have something like this. Just going to write it like that. And they could ask you to draw an isomer of that, and some people really struggle to think, oh, well, I can't see what I could possibly do. And all you need to do, and that's why it's like it's not a, hopefully once you see it once, you'll be fine, is to just swap or reverse around the ester group. You can see where the carbonyl is in relation to the two R groups. So yeah, this example actually didn't really, the example of the question on the page didn't really highlight that, but just watch out for that. If you're given one ester and you're asked to draw an isomer and you really can't see, then the first thing to try is just to swap the COOH round to put the carbonyl group on the other side and the single bonded oxygen on, just reverse it like I've done here in this one at the bottom. Okay, so still now, well, thinking about the equilibrium as an equilibrium, we saw that if we looked at it as in the direction of alcohol plus carboxylic acid goes to ester and water, that was an esterification reaction and that was a condensation reaction. But something to bear in mind with any equilibrium reaction is that they are going forwards and backwards. So we can simply reverse the equilibria, we can simply reverse the equation and it's still an equilibrium equation. So this time we're looking at it, if you go towards the bottom, as an ester plus water goes to alcohol plus carboxylic acid. It's exactly the same as what's above. It's an equilibrium reaction, only this time we're not thinking of it, because we're reading it from left to right, we're not thinking of it as a condensation reaction, as an esterification reaction. We're now thinking of it as a hydrolysis reaction. So if we look at it going from ester and water to alcohol and carboxylic acid, then we are breaking the ester group apart. And we can do that, we can think of that. So what I'm trying to say, I guess, is that you can consider about making an ester. So you can put an alcohol and a carboxylic acid together, and then if you leave it for long enough, and it is quite a slow reaction even with an acid catalyst, you will reach a point of equilibrium at some point in which you now have a mixture containing alcohol, carboxylic acid, ester and water, plus don't forget the concentrated sulfuric acid as well. You could start with an ester and water, and so you could add an ester and water together, and again you could use an acid catalyst. So that's what we're talking about when we say acid hydrolysis. I'm just referring to the acid hydrolysis. We could then wait again a while until equilibrium is reached, and we would have gone from just having an ester and water to having now a mixture of ester, water, alcohol, and carboxylic acid. So you can approach the reaction from either side. One of them is an esterification reaction, that's a condensation reaction, and the other one is hydrolysis. So we need to look at those two hydrolysis reactions a little bit more carefully. Now, the acid hydrolysis reaction is no different than the formation of the ester. We're just starting from the other side. We add concentrated sulfuric acid, although in this instance we would perhaps heat under reflux to speed up the rate of reaction and to reach equilibrium faster, although I don't know, it doesn't sound like absolutely ideal, does it? But still, that's the accepted norm. Much more interesting though for us here is the alkaline hydrolysis. So regarding the acid hydrolysis, just the point is that you can, if you've got your equilibrium reaction, you can start from either side, right, depending on your reagents. Now the alkaline hydrolysis is a little bit different, as we'll see. So here we've got our ester and we're adding an alkali, sodium hydroxide, and we're getting our alcohol, but we're not getting a carboxylic acid as a second product, we're getting a carboxylic acid salt. So our example here is we've started with propyl ethanoate, we're reacting it with sodium hydroxide, and we're making propan-1-ol and sodium ethanoate. So we've got our carboxylic acid salt there. Now, very important, this method is not in equilibrium. Notice that I've drawn just a single arrow. And the reason for this is that essentially what's happening is you would have added excess alkali, and the moment that the carboxylic acid is formed through the hydrolysis of the ester, that carboxylic acid is going to react with excess alkali. There's going to be a neutralization reaction happening, therefore, and we're going to get the carboxylate salt. And if you think about how equilibria work, what we are effectively doing is we are removing, or we are reducing concentration or whatever, one of the products, if we're looking at it in this direction. And so the Le Chatelier says that if there's a change in the conditions, the system seeks to oppose that change. So what happens is, because you're removing the carboxylic acid, the moment it's formed, the reaction is constantly being driven to the right, and it gets driven, providing you have excess alkali, that is, it gets driven all the way to completion. So the carboxylic acid is being removed from the equilibrium mixture as it's formed. That means the ester hydrolysis continues and continues and continues to completion, as long as you've got excess alkali. And so it is different than the acid hydrolysis. And another thing to just sort of stress is that in the acid hydrolysis, the acid was acting, or is acting, as a catalyst. It's acting in the same way, that is, if we started with the alcohol and carboxylic acid. Here, however, in alkali hydrolysis, the alkali is actually reacting and is not being regenerated, and so it is not acting catalytically. So thinking about uses of esters, they're used as solvents, perfumes, and we're going to flavourings. We're going to look at that briefly in a second, and then plasticizers. And I've written a little bit of more explanation about plasticizers because it is something that was a feature of the polymers part of alkenes, but it's almost like a fact. It's like a single fact. It's quite easy to forget. It's quite easy to not remember. So it's typically esters that are used as plasticizers, and essentially these are molecules that get between polymer chains, and if they get between them, then they weaken the attractions between the chains, and it tends to make the polymer more flexible, which is why you can get PVC clothing, which therefore must be flexible, but you can also get PVC guttering, which clearly is not very flexible. So that would be the difference. There would be the use of a plasticizer, which may be an ester, but that's commonly what they might be used for. So esters are very much looking at artificial and natural flavourings. There's like a collection of fruit here, and the molecules that give them, or give some aspects of those flavourings, you can see are all esters, or a lot of them, or the ones that we're showing here are esters. Then obviously with solvents, plasticizers, so there, you've got a plastic ruler that can be bent. doesn't shatter, it's not brittle, and then perfumes, obviously. And that concludes the, well, it includes the esters part of the carboxylic acids and their derivatives, as where we're exclusively looking at esters. We're now going to look at lipids, or which are oils and fats. They are going to feature esters, but we're looking at them in the context of vegetable oils and animal fats. Okay, so this isn't a huge topic. It is one though that I think sometimes people find a little hard to get their head around. I guess it's because it's one of those areas where you've got to just sort of remember what you're doing, and it is about understanding, but that's not maybe what it feels like. So it is important to sort of pay attention at this point and really try and get your head around it. And if you're struggling with it, then you need to do something about it and ask me for help or whatever. But it's don't let it slip by, because what tends to happen is people just get a block about it, and that block stays and stays and stays, and then it's quite difficult to get it back. But it's not that difficult, and we can definitely make it something that you can feel very comfortable about. Right, so vegetable oils, animal fats, they are a type of ester, and they are most often a triglyceride. And as far as the chemistry course is concerned, we're only going to focus on a triglyceride. So that's what I'm going to draw now, so we can see what a triglyceride looks like. Okay, so there's our triglyceride. So a few things to just point out. It has a backbone, or what we can think of as a backbone. Do pay attention to the way the ester group is done. So if we're thinking about that backbone, the backbone must be attached to the single bonded oxygen. Right. So just remember that is how the ester is, the direction of the ester group, as it were. And then we've got these R groups, and those R groups can be the same. So I've written RRR. But actually, so you've got to pay attention depending on you've got to look at the question and look at the information you're given. They could be the same. That's why I've written R 3 times, or they could be all different. Okay, so just bear that in mind. Okay, so that's a triglyceride. You can see it's got the ester group. You can see why it might be called tri, because we've got these 3 ester sort of chains. And the glyceride bit we're just going to come to in a second. You'll understand, why the glyceride bit is part of the name. I've never known you to have to ever name something or identify it as a triglyceride. It's just that is what we're looking at here. Now, we saw with esters that you can hydrolyze them, or they can undergo hydrolysis. And if we just hydrolyze them in a sort of simple way, that's using water. So if you think about fats, they will go off over time. They will go rancid, especially, and if there's a lot of water or if there's moisture around, then that's going to happen more quickly. So we can use water to make this happen. And we've got 3 ester groups, so we're going to need 3 water molecules, and that is going to give us 2 products. Now, we're going to look at a couple of types of hydrolysis reactions with triglycerides, but one thing that we always get is what is called glycerol, and glycerol has this structure. So glycerol is always made, and you can see that it is the sort of backbone part of the molecule that has formed the glycerol there. So you can see that the ester group has been split or broken, where I've drawn this green squiggles here. So we get glycerol, and then the other product that we get are fatty acids, or what are called fatty acids, but essentially they're carboxylic acids. They're just very long chain carboxylic acids, and we've made them from a triglyceride, so we're calling them fatty acids. So the 3 so what we produce, as well as the glycerol, is shown here. If that R group in our triglyceride had been the same, I would have written 3 and then RCOOH. But I wanted to emphasize that you've got to watch out for the R groups, and they may be the same, they may be different, so just watch out for it. So I've got 3 different fatty acids in this example here. So just to make it clear that they are called fatty acids. Now, they have asked questions about the hydrolysis of oils and fats where it's only been water. But typically where they tend to focus their attention is if we use different reagents, so different to water, and the products from using those different reagents, depending on which one we use, it could be soap or it could be biodiesel. The fundamental reaction is the same, so we're always going to get glycerol and we're always going to have the ester breaking in that place, but our product as well, in addition to the glycerol, are going to be slightly different, or they're going to have different uses. So we'll look at making soap first. I need to draw the triglyceride, the fat that we're going to use. And if you think about it, a lot of the soaps, you can get soap that's been made out of olive oil or coconut oil or animal fat, actually, or so on. So you can see this is the saponification. This reaction that we're about to see has been fundamental to the production of those soaps. Okay, so there's our triglyceride as before, and this time what we're going to react it with is sodium hydroxide. So it's our alkali hydrolysis that we saw with our ester. We've got 3 ester linkages, so we need to use a molar ratio of 1 to 3, triglyceride to sodium hydroxide. And then we get as our products, well, we're going to get, as we always do, glycerol. Okay, always get that. So it's always a product, so bear that in mind. And we'll look at the UPAC name of that in a second. I perhaps should have mentioned it on the previous slide. And then our products, our other products, are going to be salts. So we've made 3 salts, and it's those salts that are the soap. So obviously bear in mind, when you're talking about in water, the sodium ions and the carboxylate ions will be separate. So yeah, we got our glycerol. Now, you could be asked about the UPAC name. So, pause the video, have a think about the UPAC name for glycerol. So just pause it. So hopefully you saw that it was propan 1,2,3 triol. So that is a sort of a question, I suppose, that can be asked, like with the lactic acid earlier. So that's making soap. So if you use sodium hydroxide with your triglyceride, with your animal fat, vegetable oil, then you get glycerol and you get soap. So a sort of quick description of how they work. So they basically have 2 ends. So they have the carboxylate end, which is a hydrophilic end. So that's attracted to water, and it's attracted to water. And then when you have that very large R group, that very large alkyl chain, so that's hydrophobic. And so basically the hydrophobic bit buries itself in the oil or fat or grease or whatever, and the hydrophilic end is sort of like dissolved in the water, and it is essentially produces just very, very small droplets of fat, which can then much easier to wash away. So I don't know if you've ever put a frying pan into the washing basin, and you've got like a big, you can see the big sort of slick of oil or fat, if that's what you've got in your pan. And then if you then add a few drops of if you do it, so rather than adding it to soapy water, if you put it to water, you see your fat or oil that's sort of floating on the top of the water. If you then add a few drops of your washing up liquids, so what you'll see is the fat suddenly sort of seems to break up and disperse. It doesn't disappear, because where does it go? But if you look closely, you'll then find that it's now in very, very small droplets, and it's much easier to dispose of, and also to liberate or get away from anything else that it's stuck onto. So that's essentially how a soap works. You don't I've never known you to be asked about how a soap works, but you do need to know about the reaction to make soap, which is what we looked at on the previous slide. And then lastly, we can use vegetable oils to make biodiesel. So again, this is a hydrolysis reaction. Again, we're starting with a triglyceride. Only this time we're going to react it with methanol. And obviously we're going to be breaking 3 linkages, so we need 3 methanol molecules. And we get, as we always get, we get our glycerol. Okay, so you always get that. And then the other product that we get are as the title says, 3-methyl esters. Those methyl esters are the biodiesel, and just to make it clear, this is the methanol, and that is the source of the methyl that's part of the new esters. Okay, so that's how we make biodiesel, and then once we have biodiesel, we can use it as a fuel. Standard combustion reaction. So we just got a molecular formula here of a methyl ester. React it with oxygen, and naturally it produces carbon dioxide and water. But of course, if our vegetable oil has been grown, from a crop, which it obviously has been, then we are producing something which, whilst maybe not carbon neutral, has a much lower impact on the amount of carbon dioxide in the atmosphere. And that concludes the first part of carboxylic acids and their derivatives. So we've looked at carboxylic acids in general. We've reminded ourselves that they are acids and therefore can undergo any reaction that any other acid could undergo. We sort of went then into esters, which was the first of the derivatives, and we looked at the fact that there's an equilibrium reaction, what the conditions are to produce an ester. Then also, if we were looking at the reaction in the reverse, esters were undergoing hydrolysis, and we looked at acid and alkali hydrolysis, and they don't have the same effect, as it were. And then we moved on to vegetable oils and animal fats, or lipids, and really, which was sort of an applied hydrolysis of esters. It's sort of an applied approach where we can make soaps or we can make biodiesel. And so that's a big chunk of carboxylic acids. So we've still got something called acylation. So we've still got the actual mechanism to do with carboxylic acids and their derivatives to do. So that's going to be the next video about carboxylic acids. But yeah, if you have any questions or queries, just let me know.